In this video and in the video after this one, I want to tell you about some of the practical tricks for making gradient descent work well. In this video, I want to tell you about an idea called feature scaling. Here's the idea. If you have a problem where you have multiple features, if you make sure that the features are on a similar scale, by which I mean make sure that the different features take on similar ranges of values, then gradient descent can converge more quickly. Concretely, let's say you have a problem with two features where x1 is the size of a house and takes on values between, say, 0 to 2000, and x2 is the number of bedrooms, and maybe that takes on values between 1 and 5. If you plot the contours of the cost function j of theta, then the contours may look like this, where, let's see, j of theta is a function of parameters theta 0, theta 1, and theta 2. I'm going to ignore theta 0, so let's forget about theta 0 and pretend it's a function of only theta 1 and theta 2. But if x1 can take on a much larger range of values than x2, it turns out that the contours of the cost function j of theta can take on this sort of a very, very skewed elliptical shape. Except that with a sort of 2000 to 5 ratio, it can be even more skewed. So this very, very tall and skinny ellipses, or these very tall skinny ovals, can form the contours of the cost function j of theta. And if you run gradient descent on this sort of cost function, your gradients may end up taking a long time and can sort of oscillate back and forth, and it can take a long time before it can finally find its way to the global minimum. In fact, you can imagine if these contours were exaggerated even more, if we were to draw incredibly skinny, tall, skinny contours, and it can be even more extreme than that, then gradient descent can just, well, it turns out gradient descent will just have a much harder time taking its way, meandering around. It can take a long time to find its way to the global minimum. In these settings, a useful thing to do is to scale the features. Concretely, if you instead define the feature x1 to be the size of the house divided by 2000 and define x2 to be maybe the number of bedrooms divided by 5, then the contours of the cost function j can become much less skewed, so the contours may look more like circles. And if you run gradient descent on a cost function like this, then gradient descent, you can show mathematically, can find a much more direct path to the global minimum rather than taking a much more convoluted path where it's sort of trying to follow a much more complicated trajectory to get to the global minimum. So by scaling the features so that they take on similar ranges of values, in this example we end up with both features x1 and x2 between 0 and 1. You can wind up with an implementation of gradient descent that can converge much faster. More generally, when we're performing feature scaling, what we often want to do is get every feature into approximately a -1 to +1 range. And concretely, your feature x0, that's always equal to 1, so that's already in that range. But you may end up dividing other features by different numbers to get them into this range. And the numbers -1 and +1 aren't too important. So if you have a feature, x1, that winds up being between 0 and 3, say, that's not a problem. Or if you end up having a different feature that winds up being between, -2 and positive 0.5, again, this is close enough to -1 and +1 that, that's fine. I think that's fine. It's only if you have a different feature, say x3, that is between, say, that ranges from -100 to +100, then this is a very different range of values than -1 and +1. So this might be a less well-scaled feature. And similarly, if your features take on a very, very small range of values, so if x4 takes on values between -0.0001 and positive 0.0001, then again, this takes on a much smaller range of values than the -1 to +1 range. And again, I would consider this feature poorly scaled. So you want the range of values, it can be a bit bigger than +1, a bit smaller than +1, but just not much bigger like +100 here, and not too much smaller like 0.001 over there. Different people have different rules of thumb, but the one that I use is that if a feature takes on a range of values from, say, -3 to +3, I usually think that should be just fine. But maybe if it takes on much larger values than +3 or -3, I might start to worry. And if it takes on values from, say, -1/3 to 1/3, I think that's fine too. Or 0 to 1/3, or -1/3 to 0. Or just that's typical range of values I consider okay. But if it takes on a much tinier range of values like x4 here, then again I might start to worry. So the take-home message is don't worry if your features are not exactly on the same scale or exactly in the same range of values, but so long as they're all close enough to this, gradient descent should work okay. In addition to dividing by sort of the maximum value, when performing feature scaling, sometimes people will also do what's called mean normalization. And what I mean by that is that you might take a feature xi and replace it with xi minus mu I to make your features have approximately 0 mean. And obviously we won't apply this to the feature x0 because the feature x0 is always equal to 1, so it cannot have an average of value of 0. But concretely, for other features, if the range of sizes of a house takes on values between 0 to 2000, and if the average size of a house is equal to 1000, then you might use this formula, set the feature x1 to be the size minus the average value divided by 2000. And similarly, if on average, if your houses have 1 to 5 bedrooms, and if on average a house has, say, 2 bedrooms, then you might use this formula to mean normalize your second feature x2. In both of these cases, you therefore wind up with features x1 and x2 that can take on values roughly between -0.5 and +0.5. It's actually not true. x2 can actually be slightly larger than 0.5, but close enough. And the more general rule is that you might take a feature x1 and replace it with x1 minus mu1 over s1, where to define these terms, mu1 is the average value of x1 in the training set, and s1 is the range of values of that feature. And by range I mean, let's say, the maximum value minus the minimum value. Or for those of you that know what the standard deviation of a variable is, setting s1 to be the standard deviation of the variable would be fine too, but taking this max minus min would be fine. And similarly for the second feature x2, you replace x2 with this sort of subtract the mean of the feature and divide it by the range of values, meaning the max minus min. And this sort of formula will get your features, maybe not exactly, but maybe roughly into these sorts of ranges. And by the way, for those of you that are being super careful, technically, if we're taking the range as max minus min, this 5 here would actually become a 4. So if max is 5, min is 1, then the range of bedroom values is actually equal to 4. But all of these are approximate, and any value that gets the features into anything close to these sorts of ranges will do fine. And the feature scaling doesn't have to be too exact in order to get gradient descent to run quite a lot faster. So now you know about feature scaling, and if you apply this simple trick, it can make gradient descent run much faster and converge in a lot fewer iterations. That was feature scaling. In the next video, I'll tell you about another trick to make gradient descent work well in practice.